so at some instant in time when x of t is greater than 0, I'm drawing the free body diagram of the spring. The spring is being stretched by the spring force. And you know from Hooke's law and from basic dynamics that the spring force is the stiffness of the spring times the displacement of the spring, and in this case it is k times x. This is for x of t greater than 0. I need to see the exact notation here. Okay, I'll just complete this and then I'll answer all your questions. I need to see this. I need to see the spring force. I'm going to draw the free body diagram of the mass right next to the spring. It's constrained in the vertical direction, so I'm going to have the weight of the mass and some normal force. We don't really care about it, they're balanced. There is no motion in the vertical direction. Then the spring is connected to the mass. If the spring is in tension, the spring is trying to pull the mass to the left. So the spring force is going to be the same thing but in the opposite direction of the mass. Applied force on the mass is F of t. This is the free body diagram. One more thing is the kinetic diagram of the mass acceleration diagram. You draw it right next to the free body diagram. And on the kinetic diagram, you mark the inertial force on the mass. If it's a particle, the inertial force is mass times acceleration. You mark the force in the same direction as a positive sign convention. Do not change this, no matter who you are. Mass times x double dot. This is the kinetic diagram, and then you bring out force balance. Sum of all the forces on the free body diagram is equal to sum of all the forces on the kinetic diagram, and this is the free body diagram. Forces pointing to the right are positive. Forces pointing to the right are positive. Look at the free body diagram. I am not interested in the vertical forces because no big deal, right? They're all balanced. Horizontal forces, minus Fs, plus F of t. You see, F of t is positive because it's pointing in the same direction as a positive displacement. Beautiful. Those are all the forces in a horizontal direction. On the kinetic diagram, what are the forces? Mass times the acceleration of this block, which is m times x double dot. Rearrange the furniture. Mx double dot plus Fs, which is k times x. I bring the minus Fs to this other side. I write all the dependent variables and its derivatives on one side of the ODE, the standard form, don't forget it. All dependent variables and its derivatives on one side. All the independent variables, functions of time, inputs, they're on the other side. So mx double dot plus Fs, which means it's k times x, is equal to f of t This is a second order ordinary differential equation. We expected that with x of t as a dependent variable, and this is called the equation of motion of the system. Or EOM of the system. The equation of motion, bear with me for a few more minutes, we are not done, it's not 1:35 yet. Equation of motion is an ordinary differential equation which upon solving will tell me how the system behaves as a function of time. So we are at the last step of the system dynamics process. We have had the physical model, which is the spring and a mass. We have applied Newton's laws, which is essentially balance of forces, and we've come up with a mathematical model. All we need to do is solve it. One thing I want to point out, for any system, the number of degrees of freedom is equal to the number of equations of motion you obtain. Okay? So I want to write that statement right here. Number of equations of motion is equal to the number of degrees of freedom. So if I have 1 degree of freedom, which is x of t, I end up with 1 equation of motion. I take two masses, connect them by a spring, they can move independent of each other. That's going to give me two differential equations of motion, because I have 2 degrees of freedom, which is what I'm going to be doing at the next class. And people with questions, more than happy to answer them right now. You can come and talk to me right here. Okay? Because the accounts for the sign convention. The equation accounts for the sign convention. So that's why it goes up. You have to draw it. The direction shows all the sign
That joke never had any
You are assuming that forces that are pointing to the right are positive. So this is the force that's pointing to the right, as drawn here. Oh, because I'm assuming it will be pointing to the right. I start off by saying, okay, I'm going to draw this entire thing using the positive sign and obtain the equation of motion. If upon solving, I end up getting x of t to be negative, it means the body is going exactly. So there was, I think he was there before you. Yes. Oh, no, not like that. So I just said take the solution, substitute, plug it in and see if it gives you the right answer. Okay. Do the next one. No, so the time invariance is only when you look at coefficients, not the dependent variable. Right. So I could, for example, have 7 times z of t times z dot of t. That would still be a constant coefficient, because the z times z dot is the product of the dependent variable. They are not coefficients of these.
Oh yeah. No, we're going. If it's empty, we're going out the main one. There's no point.
Depends. Absolutely. So if I could, so same thing. Yeah. I could say that this is the positive direction of x of t. Now, let's say the force is negative will be tangent, positive will become so an equation of motion.
Doesn't say right there.
Minus f. So next class I'm just going to do something completely random and then end up with something similar.
I just want to make sure it wasn't.
No, there's no hard and fast. But it's some choices are better than others.
Right.
So you can think of it as, okay, this is the force that causes the mass to move here. But what if I have like a lot of force? I don't really know whether it has to do with that or not. So what I'm saying is, okay, let's use a coordinate. Set up x of t to be positive if you spring is an object. Then draw the force for this situation. Draw these as their views. And then write the equation of it. If you get a positive value for x of t, how to solve it, then it takes a negative.
So just to make it flat, I don't want to now is that that's great.
For x of t, let's say. Yeah, so the spring element is connected to Yes, absolutely. That's the point. I forgot to make that point, but the spring element